So, a couple of things off the top. So, apologize for the abrupt ending to last class. Hopefully, things are normal for the next 4 to 6 weeks. But if not, keeping an eye on Canvas for announcements. So that's going to be how I'm going to communicate to you outside of class. I don't anticipate, hopefully, any more classes being canceled until hopefully mid-November. But kind of keep an eye out on that. I'll kind of not just use it for me not maybe being in class one day, but also things related to class. So like yesterday, kind of put up that, that quiz and problem set were a little bit delayed. I haven't gotten that practice exam up. You should see that pop up this afternoon. I'll get that kind of uploaded. But you do have that third quiz and problem set. So the problem set's going to be due that Tuesday before our exam on the 17th. That's in-class exam. The quiz will be due at the end of next Friday. So I want you to kind of get on and get that done a little bit sooner. So that's why I put the due date a little bit quicker on that quiz. You've also had the practice problems for a little bit now. And that problem set, I would not suggest waiting until that Monday of exam week to start working on it, right? I would try to get that done well in advance of the due date, but I realize everybody has different schedules. And so I do want to kind of give you a pretty good amount of time to work on that, okay? Also, before I forget, I will have office hours tomorrow. I'll be in my office from 1 to 4. So if you want to stop by tomorrow, I will be there if you have any questions over that practice or problem set or anything else. And I'll get an announcement posted up about that as well after class. Okay. Let me think. That should be everything. Any questions from me before we kind of jump into material here today? Okay. So I believe, if I remember correctly, we did kind of get through everything kind of in the slides, right? We're just about to kind of transition to looking at how we do apply a lot of this in this data. So we really shouldn't be too bad. I mean, next week we'll really be doing review. So we lost a little bit of time on Tuesday. I probably won't work through quite as many examples today or this week as I planned, but I'll just save those for next week because really we just want to be rehashing the same topics we're talking about with multiple linear regression, as well as going back to some of that earlier stuff that we kind of had, review of probability and statistics, some basic linear regression stuff that we maybe have gotten a little bit away from, but just really seeing more examples throughout the next 3 class periods, like leading into that exam, okay? So, and I'm remembering correctly, we kind of looked at this F statistic, we just haven't really seen how we do this data yet. So we'll go to Stata here starting out today. I've got that MLR inference do file pulled open, so that's what we'll start out with. I'm going to define my global. If you didn't want to, you could always go to File, Open. We're going to use this star public use data set. So I'm going to open that up. Once again, if I didn't want to use that global, I could just copy this command over into my view file. Right? So I'm going to just kind of use that same file. We're going to start out thinking about if we had a very basic regression where I'm trying to predict college GPAs in year 1, and I've only got an identifier for whether or not the individual is female, and I've got their age. So pretty naive regression, probably a lot of important omitted variables. We're going to do some joint hypothesis testing today that we talked about we had in class on Tuesday. So kind of make a couple of points though along the way. So if I run this I'll run it again so it looks a little bit prettier. I'm actually going to make this a little bit new. So if I run this regression, right, we said, as we add in more variables, what should be happening to our R-squared? So the proportion of variation in our Y variable we can explain, if I'm including more independent variables or explanatory variables, what should happen to the proportion I can explain? Go up, right? So we always know our R-squared was going to go up, but our adjusted R-squared accounted for the fact that, we can't just start adding in variables that don't matter. And so we're going to penalize ourselves for the number of variables we were adding in, right? So kind of the difference in between our adjusted R-squared and R-squared, I want to make a couple points about that before we get any further. So we'll switch over to the dot cam here. All right. So, and also I'll point out on Canvas where this is at. But for that exam, you'll have a formula sheet with any formula that we've used throughout this whole time. So it's already up there. You can kind of see it. There's a PDF version of it. So as you're studying, maybe print that out. You'll kind of know what you'll have for the exam to look at. We said our R-squared, right, is just going to be the proportion of the variation in our Y variable we can explain. Another way of writing that is 1 minus the proportion that we can't explain, right? So the proportion that's unexplained, that was our residual sum of squares, right? How much we weren't explaining. Now our adjusted R squared is that exact same equation. However, we scale that proportion that we can't explain by a factor, right? What that factor was n minus 1 over n minus k minus 1, okay? So we said a couple things. As I add in more independent variables, so k was the number of independent variables we included in the regression. What's going to be happening to my denominator here? I'm subtracting a larger value, so my denominator is getting smaller. If my denominator is getting smaller, what's happening to this fraction? It's getting larger. If I'm subtracting a larger value, my adjusted R squared is getting smaller. So adding more variables there on the right-hand side is going to decrease that adjusted R squared. So there'll always be the adjusted R squared is a little bit lower than our regular R squared, right? Because this fraction will always be greater than 1. We can kind of think about how then the sample size might impact that difference. So let's think about a sample size of 3, and I only have one variable, just to make it easy. So 3 minus 1 is 2. 3 minus 1 would be what? 1. So that factor, that fraction would be 2. Well, what if I had a sample size, same one independent variable, but had a sample size of 100? Well, then it would be 99 over 98. Notice this is going to be a lot closer to what? 1. As my sample size goes up, this scaling factor gets closer and closer to 1. So in fact, when I have a really large sample size, this is approximately 1. What ends up happening to my R squared and adjusted R squared? They basically end up being the exact same thing. Okay? So that gap in between our adjusted R squared and our R squared is going to be getting smaller when we have larger sample sizes. So if we look here, not here, we look here, right? We've got a pretty large sample size. So what's happening to that gap in between? You can't see that. So we got a pretty large sample size. So what's happening to that gap in between our R squared and our adjusted R squared? If I move the mouse, pretty small, okay? And I'll kind of try to point this out later, what happens when we have smaller sample sizes if we get there. If not, we'll kind of go through that again on Tuesday. So just revisiting some old topics before we kind of go to what we were talking about last class, which is if I'm adding in additional control variables, right, I might want to test for whether or not they're what we call jointly significant. So let's see here. I don't want to do the small sample size one yet. I'll just add to this one. This is fine. So let's say GPA 0 and work 1, right? So I'm going to add in just 2 more variables into my regression. So I'm just going to copy and paste this. And the variables that I want to include are GPA 0, which I believe, and I think I rename it later in this file, is just there. Let's see if that's pretty sure it's just, yeah, rename it later on, but it's just their high school GPA. So I'm going to add in these 2 additional variables, kind of run my regression. What should happen to my R squared? It should go up. So 0.15, it is now 0.19. So as I add in more of these independent variables, it's going to increase my R squared. But what we were doing with joint significance testing is essentially saying, yes, we know that if we add in more variables, my R squared will be higher. But did it change my R squared in a statistically significant way? Or is the amount of additional variation I can explain and why with these new added variables, is it statistically significant? Okay. So what we were doing, this as a reminder, we had this equation, which is we can calculate our F statistic, right? So we said when we add in more variables, we always know the R squared is going to go up. So we had this F distribution where we were only looking at the right tail because we know that the difference between our new R squared and the old one will always be a positive difference, right? It has to be going up. So just to kind of connect this to some things we've already talked about, how would you calculate a test statistic for a slope coefficient? It was a pretty easy equation. All we did was take that slope coefficient and divide it by what?
Standard error.
Yeah, the standard error of that estimate. Okay. Now, kind of behind the scenes, what was in that standard error? There was a bunch of stuff here and then an n-2. And then remember, when we're doing test statistics for sample means, let's assume that we had an assumed true population mean of 0, right? We would kind of plug a 0 in here. We divide it by the sample variance. Well, what was in that sample variance? An n-1. So we're always dividing by some form of that sample size, right? And these standard deviations called, with our test statistics, standard errors. So another way of thinking about that is it's your standard deviation of that slope coefficient. It's not technically the correct terminology, but it's easier to think about it that way. So the statistic that we're now interested in is not the sample mean. It's not the slope coefficient. It's the change in our R squared. So based off of our two regressions, is that change in our R squared, so the unrestricted model, where we include more variables, the difference between that and the R squared of our restricted model. Right? Now we did something slightly different here, which is we divided that difference by the number of restrictions that we had, or the number of additional variables we were adding in to that unrestricted model. Okay. We then we're going to divide that by, kind of think about here, this is going to represent like a standard deviation of the difference in our R squared. That isn't quite technically the best way of saying it, but I think it'll help kind of connect the dots between all these different types of test statistics. So what we had in our denominator was 1 minus the R squared from the unrestricted model, and then divide that by n minus k minus 1. So notice here we had like divide by n minus 1, n minus 2. Now divide by n minus k minus 1, where k was the number of variables in our unrestricted regression. Okay. So this is what we're going to be using. We'll kind of look at how we would do this in Stata, right? There's actually an easier way. We don't have to always calculate it manually, but we can. Okay. So if we looked at this output, we've got our sample size. We've got our R squared. We've got our R squared from the unrestricted model where we added in these two new additional variables. That's everything we needed. The only other thing is how many restrictions did we have? Well, we had female and age. Here we were adding 2 more variables, so Q is 2. How many variables do we include in the unrestricted model? We had 4, right? So K is 4. Now it's just a matter of getting those plugged into our calculator, right? So I don't think I have it typed out in the comments, but this is maybe a good time to kind of practice how we could do answers to problem sets. So let me see here. I'm going to move this over here and move this over here. So for our unrestricted, can I get this all in one line? Let's see. It'd be really nice if I could. There we go. So this top one was our restricted model. The bottom one was our unrestricted model. So if I want to calculate my F statistic, it's going to be what? The difference between my unrestricted model's R squared. And here we're not using the adjusted, we're using the actual R squared. Right? The difference between that and the R squared from our first model, right, our restricted model. So here we found a pretty large difference, right? So I'm going to guess that like this is going to be highly statistically significant, or we're going to have a very large test statistic, small p-value. But I got to kind of finish this out. What is Q? I left 2 things out of my regression. Whoops. I'm then going to divide that by, what do we have? 1 minus the R squared from our unrestricted model, so 0.1956. We then divided that by n minus k minus 1. So here, this one is a little bit weird, and I'll explain in a second. I'm going to use the lower sample size here. In practice, when I give you these data sets for problem sets or on the exam, I make sure that it's going to keep the sample sizes the same between the restricted and unrestricted model. This is sometimes a data issue if we just have missing values. So any data set I give you guys for homework sets or I use for like quiz questions, I always kind of throw out any missing values so that those sample sizes would always be the same. But once we have all this, now it's just a matter of getting this plugged into our calculator. Okay. Now, I can't look at these numbers and think of exactly what this F statistic is, but there's a nice shortcut that we can use in Stata to find it for us. So anytime you run the unrestricted model, if we use this test command, right, we can test the joint significance for any variables that we've included. So I'm going to do, the ones that we added in were GPA 0, or high school GPA, and then this work 1 variable. So were these two, what this test command will do is run both the models, use the R-squareds, calculate the F statistic, show it to you, and then also calculate your p-value for it. Okay? So I'm going to run that command, and I get this. Sure enough, a very large test statistic. My F statistic here is 157. Right? So I'm saying that that difference between the R-squareds, you can kind of think about it, it's like 157 standard deviations above the mean, right? Just like we were doing with our other sample statistics. Now the p-value is basically 0. So at every single level here, I can reject the null. Remember, the null that we had when we were doing this joint significance was that whatever variables we added into that unrestricted model, that both of them simultaneously are equal to 0. So we found a p-value of 0, so we can reject that. So I'm rejecting that adding in these variables had no additional explanatory power, right? I found instead strong sample evidence that adding in these two additional variables greatly increased the proportion of the variation in that y variable I can explain. Or it greatly increased my R-squared at statistically significant levels, any level, right? Because our p-value is 0. So it's a 10, 5, 1% significance level. So it's just like what we were doing with other hypothesis tests. As long as that p-value is less than alpha, we can reject this null. Okay? Questions on that before we keep moving here? Yeah.
Can you just re-explain the difference between the restricted and unrestricted regressions?
Yeah, so we're thinking about our unrestricted model is going to be including all of the variables here, female, age, GPA, and work. Our restricted model was like this naive regression. So we started out here. So usually when you're thinking about this, like you always start out with like your restricted model. I'm only including 2 variables to try to explain college GPAs. My unrestricted model is, okay, there's these other 2 variables I think might help me make better predictions. I think they might explain more of the variation why. I'm going to add those into my regression. So when I add those 2 additional variables into my regression, this is my unrestricted model, right? It's not leaving anything out. So what I want to test for is whether or not this unrestricted model increases my R-squared. And I have a statistical test to do that, which is calculating this F statistic, coming up with a p-value, and then I can say, you know, I always know that it's going to go up. When I add in more variables, I always know the R-squared is going to increase. But is it increasing at statistically significant levels? Does that help a little bit? Okay. Sometimes just explaining things in a slightly different way is going to connect with something else. So always ask questions. So yeah, this one's pretty strong effect. Now, what you can also do, like let's say that instead I think, well, okay, maybe GPA and work look like they're good at explaining the variation in my first year of college GPA, the high school GPA. I can also do tests, joint significant tests of other variables in that regression. Now, essentially what it's doing behind the scenes is it's going to run a regression. Well, here, I'll copy and delete, copy, paste, delete. So essentially what Excel is going to be doing behind the scenes now is when I say I want to test for the joint significance of female and age, it's going to run a restricted model where it only includes high school GPA and work. It's then going to run the full unrestricted model and then use those R-squared values, K and Q end up being the same in this example, right, and calculate that F statistic. So can I say that adding in female and age has joint significance? Or do they increase my R-squared at a statistically significant level? So I can run this real quick. It does all that work behind the scenes. Okay, well, I can still say that those 2 variables have some joint significance here, right? That p-value is lower than all of my alphas. But notice the test statistic is a lot smaller, right? So, you know, even though I still can say it's increasing my R-squared at statistically significant levels, not quite as strong as the other 2, right? That F statistic or test statistic is a lot smaller. Okay. Any questions before we move? I also forgot plastic water bottles, and I hate drinking out of something this big, so I'm sure it looks awkward as hell. So let's keep going. So what if I had something like this, right? So I've got the same kind of regression I had before, but I'm now like throwing the kitchen sink at it, right? I'm including a bunch of additional variables. So what's that going to do? First of all, we'll kind of touch on two concepts, which is, so I already took it off the screen. Let's come back to it. We have, now let's think about my original regression where I was just having female and age. I'm now thinking about, do all of these additional variables, GPA all the way through mom2, which I think this is like whether the mother went to college or not, do all of these variables have joint significance? So I can think about what this is going to do to my adjusted R squared first. So we said our adjusted R squared is going to be equal to 1 minus the proportion of the variation we can't explain times n minus 1 over n minus k minus 1. Well, my sample size shouldn't be changing. I've got the same data, but I've now included more independent variables there on my right-hand side. I went from 2 to 8, right? So if k goes up, right, might be a little bit harder to see, but what's happening to this fraction, right? Well, if k is going up, I'm subtracting a larger value, so my denominator is getting smaller, right? If my denominator is getting smaller, this fraction is getting, I'm subtracting a larger value, my R squared is going, oops, down. So as I add in more independent variables there, the gap between my R squared and my adjusted R squared is growing. Okay? So we'll kind of take a look at that here in a second. But we can also think about that F statistic equation. Now it gets a little bit tricky here because adding in more restrictions is going to impact multiple things. Okay? Okay. So as I'm adding in more restrictions there, I now want to test the joint significance of 6 different variables. Well, K is going to go up. My Q, that's also going up. Now instead of 2, it's 6, right? So it's kind of hard to see exactly how adding in these additional restrictions is going to influence our F statistic. But if you think about this value is getting larger, this value is getting smaller, that fraction would be getting larger, right? However, we can't really say because as I add in more variables, this unrestricted R squared could dramatically increase, right? So I can't really say much about the way that my F statistic is going to change just by testing for more restrictions, right? In general, right? If I'm dividing my numerator by a larger value here, that should decrease this fraction. The numerator should decrease my F statistic. So it does make it more difficult to do the, make joint significance rejections if I add in more of these restrictions. The problem is, yes, adding it in operates through this denominator. Yeah, that's going to decrease my F statistic. But as I add in more variables, what's going to be happening to my unrestricted R squared? It's going to be going up quite a bit. And I have no idea about the ratio of how much it's going to increase relative to how many restrictions I'm using. Right? So we can't really say a whole lot about that, but we can, with the sample size, say what's happening to a kind of our adjusted R squared here. We can also, and I'll make this point with the data later, if I've got really large sample sizes, right? What's happening to this fraction? Dividing by a larger number, so it's going down. I'm dividing by a smaller number. What's happening to this fraction? It's going up. If my F statistic is larger, what's happening to my p-value? Yeah, someone's pointing down, right? So having larger sample sizes makes it more likely we can reject the null. So we like large sample sizes. In terms of the number of restrictions, we can't really say whether or not that's going to make it more or less likely we can reject the null. Okay, so we'll work through some examples looking at this. So here I've got K is now 6, or sorry, K is not 6. Q is now 6. K is now going to be what? 8. So I've got 1, 2, 3, 4, 5, 6, 7, 8 explanatory variables now in the restricted model. So I could run this regression. Right? Now I'm doing this instead of typing variables out. If I want to test the significance of all of these variables instead of female and age that I just added in, I'm just going to copy and paste them. Right? So I can test the joint significance of all 6 of these. So I'm going to run that test. It's going to run the restricted model, the unrestricted model behind the scenes, use the R-squared sample sizes, calculate that F statistic. And I get an F statistic of 55.93. Okay. So my F statistic here, testing for 6 restrictions, is a little bit lower than when we only had 2 and we were like at what? 500 or what was it now? 157. All right, so it's a little bit small. But in theory, it could actually go up. We're not really sure. It could go up or go down, depending on how many restrictions we want to use there. So I just wanted to show you can do this for not just 2. A lot of the examples I use, I'm just doing 2 restrictions. You can do this for as many restrictions as you want. Yeah.
I have a question. To determine whether 2 variables are statistically significant with the R-squared value, what is like a number cutoff? Like, or is there even a number cutoff?
So, yeah, types of questions I would be likely to ask you on these aren't going to be using really that critical value approach, because I don't have it pulled up. But remember, we had that F table. The critical values are going to be different for every combination of n minus k minus 1 and q that you have. So we don't have like a nice standard normal approximation like we could use for the student t. Now that last row, if we get large enough sample sizes, we can kind of say, we kind of know what those values typically will be, but it's only going to be for that, I think it was the 5% level that had that table. It was giving us the 5% significance level. So really, there's no real cutoff for your F statistic because it's all going to be dependent on your sample size, number of restrictions, number of variables you included in the unrestricted model. And so what's better to use there, we're going to just be looking at that p-value. Then it just becomes just like we were doing for any other hypothesis test. Is that p-value less than alpha? Is it less than 0.01, less than 0.05, less than 0.1? Is that what you were getting at?
Yeah.
Yeah, those, it should be, these aren't going to be wildly different than the student t and standard normal values. So like seeing an F statistic of 55 is still ridiculous because it's kind of like saying that difference in R-squared is 55 standard deviations away from a difference of 0, essentially. Right. But once we start to get to things like 2, 3, 4, it's all dependent on what the degrees of freedom is. Right. So anything over 10, probably a pretty safe bet. You're going to end up with a really low p-value. Right. And we'll run through more examples and we'll kind of see some that where we actually get p-values that aren't just 0. Any other questions here before we keep moving? Okay. All right. So we're going to come down here a little bit. What example do I want through? I sometimes put more stuff in these do files than I'm going to actually use in class, but I think there's some. Okay, let's do this one. We're going to use this star public use data set again. I'm going to rename these variables. So here, this is that line of code that I didn't have in the previous one where I make sure I kick out any missing values. Right? So this is going to make sure that if any of these variables have missing values for college dad or college mom, it's going to get rid of those. I'm then going to rename that high school GPA variable to make a little more sense. I'm using the robust command just to kind of show you here. We can actually use a combination of testing for whether or not the R-squared increased, right? We can do this joint significance test while also controlling for heteroscedastic errors. Right? So we talked before, and we'll revisit those next week. Like I said, I'll go back through older topics next week as a review for the exam. But for now, remember we said we can use that robust command. It'll deal with, and it'll kind of adjust for those heteroscedastic errors. So I'm going to run this regression where I'm trying to predict college GPAs from age, high school GPA, and whether or not the individual is identified as female. 1 if they were, 0 if not. So, my R squared is 0.1956, right? It's not the smallest, it's not the largest, right? So I'm then going to try not to, okay, there we go. I'm then going to do this additional regression where I include 2 new variables, right? So it's whether the dad went to college or whether the mom went to college, right? 1 zeros, right? So I'm adding in 2 additional control variables here, and I want to test for whether or not they're jointly significant. So my Q here, the number of restrictions I have, is going to be 2. What's my K? What's the number of variables I have in my unrestricted model? 4, 5. Okay. So I've got Q is 2. My K is 5. If I run this regression with my unrestricted model, I'll see that I've got 1,401 as my sample size. Notice, like I told you, in examples that we'll start using, I'll make sure I kick out those missing values so we get the same sample size from both. I've got my R squared from my original restricted model. I've got my R squared from my original unrestricted model. It's really just a matter of getting all those values plugged into that equation we had for our F statistic. So you'll have that formula in front of you. I might, on the quiz or the exam, ask you to calculate an F statistic. Okay? So this is how we would do it. Right? I give you the output. You identify the 2 R squareds. You have to look at the output and say, okay, how many variables were in the restricted regression? 3, unrestricted, there's 5. Okay, so the difference, the number of restrictions were 2 variables. And then how many total variables are in that unrestricted model? Now you've got everything to plug and chug, right? Just figure out what that F statistic is. So if we do that, you'll have to trust me, I guess, in the math, although I might need it later. So I'll open it up now to kind of make sure I didn't type anything into a calculator wrong. Okay. So we have about 1.56, right? So that F statistic is 1.56. So your point earlier, is that high enough? Is that low enough? Like, what's the p-value? Well, that chart's pretty incomplete. Like, I'm probably not going to be able to find exactly 1.56. It only shows me the alpha 0.05. I can't really use that table to find it. So what I'm going to do is instead use Stata to kind of produce that test statistic for me and give me my corresponding p-value. So I'm going to hit execute here. And I see, okay, 1.58. That's a little bit different than what we had, right? So why is that a little bit different? Well, the values I was using by hand, the only Stata output I can see is out to the 4th decimal. You would think it wouldn't make that much of a difference, but when we're dealing with these really small decimals, I mean, and we're dividing by relatively large sample sizes, it can make a pretty big difference. Here, it wasn't that big, but sometimes, like when we get large test statistics, the difference can be like 5 or 6, depending on the rounding. What Stata is doing is it has the R squared values stored out to whatever the last decimal. I'm sure it has some constraint. I don't think it is infinite, right? But it has it stored way further out, so it can be a little bit more precise. So 1.56, we were using the R squareds rounded to the 4th. It's using the actual R squareds. That's why it's a little bit off. Okay. So Stata results always going to be a little bit more reliable than us doing it by hand, right? But doing it by hand is still important to kind of know, being able to identify what we're actually looking at, the number of restrictions, number of independent variables that we're including, and what's going on behind the scenes in this black box, right? The stuff we can't see. So it then looks up the corresponding p-value at these 2 different degrees of freedom, and I get 0.2. So here, adding in whether or not either parent went to college, can I say that that had a statistically significant impact on the proportion of variation I can explain? Is it less than alpha? My alphas are what? 0.1, 0.05? No. So I failed to reject the null. The null is that these 2 variables that I added in have no additional explanatory power, can explain no more of the variation in that Y variable college GPA. I can't reject that. So I'm basically saying I didn't find enough evidence to suggest they have any explanatory power, that they're actually increasing my R squared at any conventional statistically significant level.
I was just gonna say in terms of like variables affecting the outcome, would you be able to tell that by their p-values and regression?
Sometimes, so for instance, it's how do I say this? It is often true, but not necessarily true. So often, if you were to look at the individual significance of each one, so here, right, those p-values are 0.3. So if I'm doing a single hypothesis test for just one of these slope coefficients, each one I'd be failing to reject. This one I'm testing for simultaneously, are they both kind of equal to 0, right? In this case, we end up not rejecting the joint significance or the individual significance. There will be instances, I think we have one later, this will be true, but especially if you're testing for like 3 or 4 variables, sometimes one of them might be individually statistically significant, but adding them all in at the same time, because we over penalize, right, that kind of minus or the divided by Q is going to lower the test statistic, we can end up not finding joint significance, even though some of the variables have individual statistical significance. Is that what you were? Yeah. Does that answer? Yeah. But more often than not, yes, like those two things tend to be positively correlated, right? But it's not necessarily true. Yep. It's a good question. So just another example here. So we actually just working through more. So here I've got one where my unrestricted model, I've just got age, high school GPA female, and it's kind of same R squared. We're starting out with the same restricted regression. I've now got these other two variables where whether or not that person worked while in college, and then this like math science credits. So, you know, if you're taking more math science credits, that's probably going to have a negative impact on your GPA. I don't know if I did it in this section. Tuesday's a bit of a blur, but you know, taking this course probably isn't as good for your GPA as taking like billiards, right? I had a student app that I had to review, and they had billiards on their transcripts. So I was like, fun times for them. So here I'm going to run my unrestricted model. Okay, my R squared went up, right? But I mean, 0.1956 to 0.1997, it didn't go up by that much. So just like when we assume the mean is 0, and I find a sample mean of 0.5, okay, that's not 0, but it's not very far away, right? So yes, we did see an increase in our R squared. It's not very far away from 0, right? Excuse me. So we could use these values, 0.1997, 0.1956, those are our R squareds. We have our sample size. We included 2 additional variables in our unrestricted model. So Q is 2, K is going to be, how many variables do we include in the restricted model, unrestricted model? 5. We could go ahead and plug everything into our F statistic, right, equation. So if we do that, I'm going to have this here. Once again, you can copy paste this into Excel. Okay, well, this one's a little bit higher than we found before. So we found a higher F statistic. So before that other example, we had our p-value was what, like 0.2? When we were doing joint significant tests for those parental college variables. So for doing the joint significance test for math science credits and whether or not they work, well, I found a larger test statistic, so I know my p-value is going to be what? Not an exact value, but yes, I'm pointing down again. If I'm getting a test statistic that's further out into my tail, what's the area in my tail? My p-value, that's becoming smaller, right? So I should have a smaller p-value. Maybe I can say that these two variables have some joint significance. So what I'm going to do is, I've already got that regression run. I'm just going to run that test command for those two new variables. Now here I get 3.7, once again, just to make this point. If I calculate this by hand, there will be some discrepancy because I'm rounding to the 4th decimal here. So there will be some discrepancy between what you see from the stated command and if you were to work it out by hand, right? Because it can be a little bit more precise, but pretty close. Now here I've got a p-value of 0.0249. So at what levels could I say that this math science credit and whether or not you worked variables while you were in college, do they increase our R squared or the amount of variation we can explain in college GPAs at what statistically significant levels? 10 and 5%. We would fail to be able to say that at the 1% level. So just like we were doing with old hypothesis testing. Once we get to that p-value, pretty easy. Okay. Any questions there? So this is also, this just brings up a good point. So I'm doing this joint significance testing. To your question earlier, Okay, I can reject at the 10 and 5% levels here, but notice that math science, individually, it was highly statistically significant, right? So just because we fail joint significance, like, doesn't necessarily mean like both variables are bad. We kind of have to use our best judgment and kind of our intuition. We're using these statistical tests, but if I'm looking at this, okay, I failed the joint significance of adding these two new variables. Maybe I didn't have them in a data set before, and now I do. And I say, oh, yeah, but adding them in doesn't really, I can't say it with 99% confidence that they increased my R squared. But if I'm looking at that unrestricted output, which of these variables looks like it probably should be included in my regression? If I'm looking at the individual significance, that math science credit one looks like it's pretty strong statistically, it has some pretty strong statistical significance. That work one looks like it's very weak, right? P-value of 0.5. So what's probably why is this not quite statistically significant at the 99% level or the 1% significance level? Well, it's probably being influenced more by that work variable than it is by the math science credits. So we want to run these joint significance tests, but they're not the end all be all. If I were to look at this, what I would probably say is, well, you know what? I probably should be running a regression where I'm not including that work variable, but I am including that math science variable, right? Any questions on that before we keep moving? Okay, I'm going to make another point here because these results seem kind of weird. So first of all, if you work while you're in college and I looked at these results and I was like, you know what? It doesn't have any impact on your grades at all. What would you say to me? You're an idiot, right? Like, of course it's going to have an impact, right? So why do we see that it's a really small impact, right? So we're going to go back to kind of revisiting an old topic. But we've got a lot of other things that probably matter, right? Our R squared was still only at like what, 0.2 or around there. We still at 80%. We can't explain the variation in college GPAs. So when we're thinking about predicting college GPA, and we had all these variables, and then one of the other variables that we had, I'll just call it beta 1 to make it easier to think about, was whether or not they worked while in college. Right? Well, the estimate that I see from my from my regression, using my sample data, should contain the true effect of working while in college, but it's also going to have some bias, right? So I'm going to think about an important omitted variable from that regression, right? So if I had some control, I might have used this one already, but it really is, to me, I think really gets at this idea of an omitted variable bias, not college. Let's say I had some measure of parental income, right? So the bias that would exist if I didn't include that in my regression would be whatever impact that would have had if I had included it in my regression times the covariance of parental income with the coefficient I'm looking at. So whether or not the student worked, and here I'm just going to abbreviate it because I'm running out of room and call it PI, right? Over the variance of that variable that we included, right? So we had this important omitted variable. So our slope coefficient was going to have the true effect plus this bias. So we can use theta output, and we'll probably dive more into examples where we're kind of reprove this to you with the data next week. But I'm always like on a quiz or exam, I can ask you about the sign of the bias, right? I can ask you about the size if I give you different output from stata, but even just as like a general thought experiment, I could just give you this regression, tell you there's this important omitted variable, parental income. What do you think the sign of that bias is? So if I'm thinking here, what impact do you think, if your parents have higher income, what impact do you think that likely is going to have on your college GPA? So maybe you could tell me a story where I'm not as worried about getting a good job and so I don't try as hard, maybe. But if your parents have more income, that probably means throughout the first 18 years of your life, you probably didn't have food insecurity. You probably had access to better resources. You probably had parents that pushed you a little bit harder in school. I find it hard pressed to believe that that wouldn't have a positive effect, right? If we look at parental income, and I have some data on this and I've read some papers. So there is a positive correlation there, right? So if we were to include it, it would have a positive effect. What's the covariance between parental income and working? Your parents have more income. I think you're more or less likely to work when you're in college. So this is going to be negative, right? So here we've got a negative bias that exists, right? So this is kind of weird. Maybe now this is going to go against my original intuition because I have a negative bias, right? In my regression, the value I see is actually going to be too low. The true effect is actually going to be larger. Well, if we go back to the results here, that work variable, it includes a negative bias. So if I were to run a regression where I included parental income, what happens? I eliminate that bias. The new slope coefficient I see is actually going to be larger, and it's so close to zero here, it actually would likely become positive, right? So it might kind of go against your original intuition that working while in college actually has a negative impact on your grades, right? But there is some studies to suggest, like if we are controlling some of these other things constant, right? So that's the effect of working if I'm holding constant age, your high school GPA, and your math science credits. So there's some evidence that, you know, having this additional thing, having the time management early on in college actually improves your time management skills and actually results in better performance in terms of college GPAs, right? I always try to, you know, I don't, you guys are older, so I don't have to hammer on you, but I teach a bunch of freshmen in my other classes. And I'm like, you know, you're all here. You didn't get here unless you're like met some level of intelligent threshold, right? Like you had to get admitted here. So you're not a dummy, right? But what's probably you're lacking that the school doesn't have as good of measures on, which is why they look at things like extracurricular activities. Because once you get to college, the downfall of a lot of people is not whether or not they can comprehend the material. It's whether or not I'm studying instead of playing video games, right? So, you know, that kind of would go along with this intuition that if we eliminate that bias, we actually see that maybe the effect of working while in college is actually positive. Anyways. All right, so let's keep moving here. Sometimes I get talking about these examples and I get excited, so I apologize if it's getting on a soapbox or anything. So kind of worked through this. We got what, 25 minutes. Let me go in here and think about what I want to work through. Well, we can start this stuff. I think this is worthwhile. So I've got this data set. In fact, I gave it to you guys, I think already as a .dta file to kind of make it easier. Importing that Excel file sometimes a little bit tougher. So I'm just going to do that instead of importing Excel to make sure I'm using the exact same data set that I gave you guys. So I've got this powerlifting data set. I don't even remember where I found it, to be completely honest. But it's like, actually, that's not true. There's some organization that collects all the data and then had it on their official website. So you don't have to know anything about powerlifting. I'll kind of talk us through a lot of these examples, and it's really just using some basic intuition. So we're not going to probably get to this. I'm just going to create this variable. We'll use it next class. The first thing we're going to start out with thinking about is I've got this regression. So the way that these powerlifting meet works is there's primarily 3 different lifts they do, and then add up the total weight lifted across all 3. And that's going to be our total kilograms lifted, right? So the total kilograms lifted across these 3 different movements. I then have the body weight of the individual in kilograms as well. So if I run this naive regression, first of all, what do you think is probably true about the slope coefficient on body weight then total?
Then it would be like positive.
Yeah, a 100-pound person probably can't lift as much as a 300-pound person, right? So if I run this regression, right? Okay, looks like for every additional kilogram of body weight, an individual can lift about 5.2 more kilograms across these 3 different movements. Okay? So it looks like there's some strong positive correlation, and my God, the test statistic's 267, highly statistically significant, right? Now, I want to be a little bit careful thinking about this because there's one, to me, before I add any more additional controls, and very obvious omitted variable. So let's say I had that total kilograms, and I was predicting it just using, and I'm going to abbreviate with body weight, just BW, okay? And that's BW in kilograms, right? So the actual, the slope coefficient I see will include the actual effect, right? But it's also going to have bias. Now, technically, there's going to be bias coming from every single important omitted variable that I have that influences y and has some correlation with the x variable I included. I'm just going to think about one of those areas of bias, right? What seems like would be a large one to me. So what was our bias kind of in general terms? We had the covariance between the variable I included, the variable I left out, divided by the variance I included. So I'll write this out in the context of our example. What if I had this important omitted variable, which was just a dummy variable for whether or not the individual was considered male or non-male? Right? Well, what do I know is probably going to be true if I were to include that omitted variable in my regression? What likely is the sign of that slope coefficient? You don't have to be politically correct here. Yeah, right? We think it's positive, right? I mean, we have tons of physiological evidence that testosterone and things like that are going to increase muscle mass. We know that this is probably going to be a positive sign, right? I like this one also because we can think about, well, what would the covariance be between that variable I left, well, sorry, I wrote them in the opposite order. Body weight and that variable we left out, which was male. Well, we know on average, males are larger, taller, higher. If we have any data set, the average weight of males in the data set will be greater than that of females, right? So we know that this covariance is positive. The variance on the variable we included, body weight, this will always be positive. So yes, we found that body weight looks like it's having this positive, right, effect or increasing the predicted total weight lifted. But maybe what that's really picking up is largely this positive bias from the fact that, well, larger body weight individuals tend to be male, right? And being male, I mean, there's different physiological advantages when it comes to just lifting weight. So if we include that variable in our regression, we can eliminate that bias. If the bias was positive, the new estimate we see will be a little bit lower, right? So, okay. Any questions on this before we go back and maybe see if this is actually the case? Because we have that variable in our data set. Copy this, maybe. There we go. Paste it, and I think it's capitalized. Yeah, we'll do male, right? Oh, come on. So now when I run this regression, it should eliminate that bias. Sure enough, instead of 5.2, I now see 3.1, right? So not quite half, but almost half of that estimate was really just a bias that was coming from the correlation of body weight with male, right? Questions on that? We keep moving. Now, what's the sign of that or size of that bias? Well, if I have these two regressions, I can easily see like, okay, I went from 5.2 to 3.15, so that's about what, 2.05? But I could have also calculated that bias, right? Because I now have what that effect of being male was on total weight lifted. So I'm thinking about, there we go. I have, this was, what did I just say? I forget what it was. 190, the effective male was 196.9, right? I can find the covariance and the variance from my data set, right? So, oops, nope, not laptop, desktop. So how can I do that? Well, we said this might look similar to something maybe on a problem set, but not covariance, sorry. Correlate, right? I want to look at the correlation between body weight and male. And I don't want the correlation, I want the covariance. So if I were to run this command, what that gives me is the covariance between the variable I included in my naive regression and the variable I omitted, right? Male and body weight. So that covariance is 5.46. And then the diagonals tell me the variances, right? The covariance of body weight with body weight, that's just the variance. So I've got the variance of the variable I included, which is 524, the covariance of the variable I included and the one that I left out. So I'm plugging those in. I've got my covariance here was what? 5.46. Variance was 524.4. If I get this plugged into my calculator, I can figure out what the size now of that bias was. Okay. So if we wanted to do that, you'd say, okay, take that 1.96.9, multiply that by the covariance, divide it by the variance of that variable I included. I get about 0.0, wait, I'd be wrong here. Oh, it's not 1.96, it's 196, right? I get about 2.05, which was the same value that I saw just comparing those two slope coefficients, right? So I kind of proved myself in the data that the bias that exists will follow that formula. Okay. Any questions on that idea before we keep? So with Stata, if I have the variable, I can always figure out what the size of the bias is. In practice, it's more likely we're going to only be able to put a sign to that bias. Okay. What else do I want to say here? Let's put that 15 minutes. I think it's worth going through this. So if I have this regression, right? And we now had body weight and then whether or not the individual was identified as male. What we're doing up to this exam is we're thinking about here, I'm estimating the relationship between body weight and total kilograms lifted, holding everything else constant, right? Now, I don't have anything else in this regression to hold constant, but if I add more things in, that's what I'm doing. My intercept, how do I interpret that? That's going to be my predicted Y value when all other variables in my regression are equal to 0. So in this case, it would be, here's the predicted weight lifted when body weight is 0 for someone who is not male. So it's kind of like your intercept, when you've included a dummy variable, is the starting point for your 0 group. And then as body weight goes up, how much is this total kilograms, the predicted total kilograms that you lift? How's that going to change? It's going to go up by whatever beta 1 is. Okay. Now, by including this additional dummy variable, what have we done? Well, now, what's the predicted body weight for someone who has 0 body weight, but they're considered male? Well, that's going to be the intercept, but now plus beta 2, right? So when I add in a dummy variable, I'm still getting the same relationship between body weight and total kilograms lifted. But for this second group, the group that's a 1, their intercept is going to be higher, or if beta 2 is negative, lower, right? So it's almost like I'm making predictions. I have 2 lines of best fit. One, where I could be making predictions for the 1 group, and the other, where I'd be making predictions for the 0 group, right? So that dummy variable is kind of like, almost in a way, this isn't technically most correct, but it's kind of like it's estimating 2 lines of best fit. Now, you'll notice I tried to draw it as a parallel shift because we're still assuming here that the relationship between body weight and total weight lifted is the same for both groups. After this exam, we'll talk about ways we can actually see, is that relationship different for both of these groups as well? But up to this point, we've just included these dummy variables. All that's telling us is like the starting point for group 1 might be a little bit higher, or if it was negative, might be a little bit lower. Okay. Any questions on this before we keep moving?
In terms of bias,
Mm-hmm.
does it negatively or positively, I guess, impact the data that you're when you talk about bias, talk about it as a variable almost, or do you re-explain what you mean by bias?
So when I use the term bias, I am talking about there is bias in our estimate, right? So because we've left out important variables, our estimates will not be correct. The way you use bias in your everyday life, probably thinking about like political stuff, people are giving you an opinion, right? It's biased towards what they believe. We're not talking about there existing bias in the data, right? We're assuming, and we'll talk a little bit about bias in the data after this exam, we're assuming the data is being collected correctly, right? Without any like collection bias. Even if that's the case, if we leave out important omitted variables, we'll still have bias in our estimates because that bias is being created not by the recording of the variables, but by the fact that we don't have one of the variables, right? So you can have bias created because people are fudging the numbers, but you can also have bias just because you don't have the numbers. That's the bias we're talking about, right? We don't have information on this other variable. We include it into our regression, so it's going to cause some bias in our estimates. Now, if we can get that variable and include it in our regression, we can completely eliminate that. Bias from like people fudging the numbers, it's a little bit, presents a lot more difficult issues, right? Is that what you're kind of getting at? Yeah. Yeah. So yeah, sorry. I use this term bias and it's very familiar to me. All we're using it is like, there's going to be basically, it's incorrect, right? Bias in our estimate isn't quite correct. Bias in the recording of variables, those variables aren't quite correct. But up to this point, we're assuming that the data has been collected without bias. Is that? Yeah. Any other questions on this before we keep moving here? All right, so I think we went through all of this. Let me think if there's anything else I want to do here. Oh, do sample size. Let's do this. We have a little bit extra time. We can do some other stuff. So. Well, and we leave, so 12:45. I'm going to add it to the homepage just so it's easy for everybody to find here real quick. So if you are in class today and you're paying any modicum of attention to me, you should get all of these extra points. So let's go. You should see that in class quiz 5. So we're going to kind of walk through some of these problems. So first one, right, and we'll touch on some old topics, but also some things we talked about today. So if I've got a regression, so I'm trying to estimate like per capita usage of cigarettes. So I've got cigarette usage measured in the number of packs. I've got cost per pack, tax per pack, and year. So we talked about when we have like dummy variables that like, we have, for instance, every level of education. We said we have perfect multicollinearity if we include all of them into our regression. That's okay. Stata can identify that. It kicks one out. We also talked about imperfect multicollinearity. So do we remember if we have two variables that are functions of each other, but not always direct, like it's not that when one is 1, the other one has to be 0. So here, if I've got tax per pack and cost per pack, as econ majors, if taxes are higher, what's going to happen to the cost? It's going to go up as well, right? You know there's some linear relationship between those two things. So you know you have some imperfect multicollinearity. Do you remember what we said that's going to do to our estimates? So the actual slope estimates we see, if we have imperfect multicollinearity, it's not going to impact the coefficients of either, but it is going to impact what? The standard error. Now we said it's definitely going to impact the standard error of one of those variables, but we also looked at a case where it can impact the standard error of both. So here, we'll kind of notice that cost and tax per pack, it looks like we got the better end of the deal because only one of the variables have very high standard errors. And I say affect, it's not only going to affect the standard errors, it's going to make them larger. And why is it a problem? Well, if the standard errors are larger, what happens to our test statistic? Remember, we take the slope coefficient, divide it by the standard error to get our test statistic. So if we have, so we have a high standard error, low test statistic, we have a lower test statistic, our p-value is higher, right? So higher standard errors, lower test statistic, higher p-value, it's less likely we're going to reject the null. Even though we know taxes per pack is definitely going to be impacting how much people decide to use, right? Well, that's because we had some imperfect multilinearity going on. So it's going to increase at least the standard errors of one variable, but it could be both, right? So it could be it could just increase the standard error of cost per pack and or tax per pack. Could be one or it could be both. Okay. So that one shouldn't be too bad. I just want to revisit that. So here I've got the cases kind of per person in terms of COVID. I have my handy Excel calculator over here. So I've got a restricted model where I only predict the number of cases using population and median household income. I then have one where I include the unemployment rate, whether or not it was considered a metro area, and the percent vaccinated in that county. I think this was county level data. Okay. So if I wanted to test for whether or not these three variables, unemployment, metro, and vaccinated, are jointly significant, right, what would I do? Well, we would go back, we have that equation. Let's see here. Zoom in a little bit more even. So we said, when we want to test for joint significance, we're really testing the sample statistic of that difference in our R squareds. So we'll take our R squared from the, where's that? There we go. Unrestricted model. So 0.8994. Subtract the R squared from our restricted model. So 0.8973. So it did go up, but looks like not a lot here, right? But we want to be able to say this at a statistically significant level. We want to actually determine what that F statistic is. So once I find the difference in my R squared, we said we divide by what? Remember, so it was Q, which represented the number of
Additional
restrictions or the number of additional variables we included in the unrestricted model. So here that was 3. So I've got my numerator. My denominator was 1 minus the R squared from my unrestricted model divided by n minus k minus 1. So here, my sample size, I made it smaller, so 100. How many variables did I have in my unrestricted model? 1, 2, 3, 4, 5. Remember, this is the y variable, so 1, 2, 3, 4, 5 of those independent variables. Then minus 1. Okay. I then got my numerator, divide that by my denominator, and I get an F statistic rounded to the second decimal of about 0.65. So this would be kind of a question that you might see pop up on like that third quiz, right, where I ask you to calculate that F statistic. Now, here I didn't get specific because I know I was going to be working through this in class. I would tell you like round to the second decimal or round to the third decimal if that's what I wanted. I'll put that in the actual problem, but here it should be 0.65. Okay. Any questions on that before we keep moving here? All right, and then the final one we have. So we talked through this a little bit earlier, just some of this. But let's say instead of 100, so the previous sample size I had was 100, let's say I get data on all counties. Okay? And there's a slight error in this question. I'll tell you what it is. I meant for it to be a select all that apply, and it did not set it up that way. So it looks at, it's treating it as a multiple choice. It was supposed to be like a multiple different answers, select all that apply. So we'll talk through, maybe there's multiple correct answers here. So which of the following is not going to be true? If we have a higher sample size, what's that going to do to our F statistic? Right? So if we go back and kind of look at the equation we had for our F statistic, I think we already even walked through it earlier. My sample size is larger. What's happening to this fraction? It's getting smaller. This is getting smaller. What's happening to this fraction? So my F statistic is going to be larger, right? So anytime I have a higher sample size, it's not just my F statistic that's going to operate through. Any test statistic I calculate, higher sample sizes will always increase that test statistic, whether it's from a student T or an F distribution. So that one's true. If we have a higher test statistic, so here, I'm thinking about rejecting the null for a single hypothesis test for a coefficient. Well, I just said increasing the sample size increases all test statistics. What does that do to all the p-values? makes them smaller. So it's going to be, if I have a smaller p-value, I will be more likely to reject. That one's true as well. So the gap in between our R squared and our adjusted R squared is going to increase or decrease. So we said we have larger sample sizes. We kind of started class like this, right? We had this multiplying kind of factor, right? We said as n gets higher and higher, what's happening to this fraction? It was getting closer and closer to 1, which made the R squared essentially, sorry, our adjusted R squared essentially the same as our R squared. So when we have higher sample sizes, that gap in between our R squared and our adjusted R squared is actually going to be decreasing. So this one's not true. Now the fourth one, we think about how are the coefficient estimates going to be influenced by my sample sizes? They're not, right? The actual estimates we come up with are based off of the data that we have, and there's really no part of the equation where we calculate it. There's no n. There's no sample size there. So our coefficients will be larger. That one's not going to be true either. We have no, they should be, in theory, if we were to take enough samples, they'd be exactly the same, right? Now, sometimes they'll be larger or smaller depending on what random sample we come up with, but there's nothing about our sample size that's going to necessarily influence our estimates one way or the other. Our coefficient estimates, sorry. Okay. So even if you're reading this and you're submitting it, don't submit it yet because we still have one more question. But if it initially doesn't show up as some of these correct, like this one, I'm going to have to go on the back end so that it accepts either one of these answers. Although I'm not super concerned with you getting the correct answers. I really just want you to kind of, I wanted some more problems to work through. What I am concerned with is today's number, okay? So today's number, when you submit this quiz, I'm telling you in advance, so don't freak out. I'm changing the number from what I originally wrote the quiz because I'm changing the number in every section that I'm in so I don't have any weird funny business going on. So I want you showing up to be getting those in-class kind of additional points, right? So I've got a way I think I can kind of test this. I'm going to change this to be kind of set to 10 points so I can tell who was in class and who wasn't, even if you ended up getting one of the questions wrong or one correct. So today's number will be 84.29, right? So for that last one, put in 84.29, submit the quiz. Once I get back to my office, I'll go on the back end. I'll just make this one worth like 10 points so I can identify from everyone's grade who was actually here and got the number correct. So even if someone wasn't here in class today and they answered the first 3 questions correct somehow, because they correctly knew I was going to go through these at the end of class, they're probably not going to get this. Theoretically, I guess they could, but I doubt it, right? So 84.29, make sure you get that submitted. I'll get those kind of updated when I get back to my office. Other than that, I'll post my additional office hours tomorrow. Just keep working through more examples, doing a review next week. Have a fun, safe weekend, and I'll see you guys on Tuesday.
I think the gap one for the number 3, is that going to be fine?
Yeah. Yeah, it was supposed to be set. So it showed, yep. See how it says like, there's like circles?
Yeah.
But I was using new, you don't care. But there's like new quizzes on Canvas and there's old quizzes. And so when I'm switching them over, sometimes the old multiple answer questions get converted to multiple choice because they now call multiple answers multiple something. So it's a little bit different. And I forgot. I'm just curious.
Go to Iron Pit.
Iron Pit?
Yeah.
No. Is that Wilmington?
Yeah, it's like I think it's like 10 minutes south.
I think I've driven by it. No, I am not. I don't live on the same schedule that I used to.